The Arctic Ocean covers the northern end of our globe. It is surrounded by land on nearly all sides, including Alaska, Greenland, and Russia. But something that makes this ocean particularly unique and important is what sits on top of this ocean, and that is sea ice. The cold Arctic temperatures lead to the surface of the ocean freezing into what we call sea ice. Historically, the Arctic basin has been fully covered by sea ice, even through most of the summer. This image is showing sea ice in the Arctic Ocean in September of last year. And this ice is a really key part of the Arctic. It serves as a habitat for many species, including polar bears. But one of the biggest reasons we might care globally about it is a property of the sea ice called albedo, and that sea ice has a very high albedo. But what is the albedo? Albedo is essentially how reflective the surface is. So basically the ratio of the reflected energy over the energy incoming from the sun. This might sound a little complicated, but it's a concept that's perhaps already intuitive. If you're going out on a very sunny day, would you want to pick the white shirt or the black shirt to wear? You'd probably want to pick the white shirt to keep you cooler. And this is because, being lighter, it will reflect more incoming energy. So this is like having a high albedo close to 1. The dark shirt will absorb a lot more energy, and you'll feel hotter because it similarly has an albedo close to 0, so very little energy is reflected. The difference between the albedo of the ocean and the sea ice leads to what we call the sea ice albedo feedback. So the open ocean, like the black shirt, appears very dark, so it has a very low albedo, 0.06, and absorbs a lot of energy. In contrast, sea ice and snow-covered sea ice have very high albedos, so they're very reflective and warm less. So this feedback is that as the sea ice melts and exposes more of the ocean below, which has a lower albedo, we'll see more melting. As you may have heard, the ice in the Arctic is declining rapidly. This video shows an animation of the sea ice area in millions of square kilometers in September of each year. So this video is extending from 1979 to last year. And what I really like about this animation is that in addition to the numbers and the plot on the top, it's also showing beneath the spatial map of the ice area, where you can see clearly the changes in the area of the ocean that are now exposed that weren't before. And so the area that's no longer ice covered in the summer, compared to the beginning of this time period, is equivalent to about half the size of the US, including Alaska. This is a large area, and with this shift from more ice-covered area to more open water areas, we expect the ice albedo feedback to come. So we can understand fairly well what the impact of fully losing ice will be for the ice albedo feedback. The sea ice generally has a high albedo, so it reflects lots of energy from the sun, stays cool, whereas the ocean is very dark with a low albedo, so it absorbs a lot of heat, gets warm, and can contribute more to the melt. But the details of this ice matter too for the energy getting into the ocean. You can see that a lot of these pieces of ice aren't really that uniform. There are pools, which we call melt ponds, that are relatively quite dark with higher albedos, or lower albedos. And this matters too. In fact, the details of the albedo matter a lot for how the melt progresses and the impacts on climate. So in order to understand how this albedo varies, we need to measure it. To measure the albedo in the field, as we call it, or on the ice, we have to go to where the ice is. So for example, I made measurements in summer 2020 as part of an expedition called MOSAiC, which was based on a large ship or research vessel called the Polar Stern. The ship drifted out in the middle of the Arctic Ocean with the ice to make observations. And in the summer, we were in the part of the Arctic referred to the Central Arctic Ocean near Greenland, which is the blue part of the line here. So we have to travel across the ice to get somewhere far from the ship, which could cause some contamination to make our measurements. We have a lot of equipment that we use to make these measurements, so we pull that behind us across the ice on sleds. This very variable surface can also make it really challenging to travel across, and so we can see sometimes that we have to cross little streams of meltwater or little hills of ice in order to ultimately get where we're going. When we get to the area we want to measure, we start to make measurements of albedo along the line. And this line has been set up to be remeasured regularly so that we can understand the details of the variability of albedo in space and also how it evolves over time, from days to months. In this video, I'm using an instrument called a spectroradiometer to measure the albedo. So this instrument, it looks like I'm holding out a wand, but at the end of that, attached by the cable, is the actual sensor, which measures light. So this sensor, you can see, is looking at this white plate, which is essentially reflecting the light back onto the sensor to make a cleaner measurement. So I decide when I want to make the measurement, when I'm set up in a good spot, the instrument is level, and then I capture that using the laptop that you can see, which is attached to my front. So the way this works to measure albedo is that we first measure the energy coming in from the sun, and then you can see I then flip it over and measure the amount that's reflected from the ice. So this ratio again gives us the albedo of how much light is being reflected. We do this in two ways. One is a bulk measurement, and that gives us the simple fraction that we've been talking about of light that's reflected. So for example, about half of the energy might be reflected by that melt pond, or that pool of water. The other way actually splits it up into different wavelengths. So for example, different colors that we can see are different waves of light with different lengths. So the fact that the ice and ponds appear blue here means that the wavelengths are being reflected differently. So all of these measurements along these lines are also coordinated with lots of other measurements that other scientists are taking on the ice, with robots below the ice, and also from helicopters above. And this all helps us understand these observations in context. Many of our measurements show how the albedo of specific parts of the ice change over time. These two photos show how measurements at the same location on two dates just over a month apart, June 21st and July 29th. So initially the albedo here was about 0.76. And what this means is that 76% of the incoming energy from the sun is being reflected by the ice and the snow. In the second photo, it's been reduced to 0.57. And these changes over this month are a result of the melting, but also lead to more melt at this location. In certain locations where we see more drastic changes in what the ice looks like, these are also associated with more dramatic changes in the albedo. So the pair of photos here now shows measurements at the same location, again on two dates over a month apart, June 22nd and July 24th. Here initially the albedo was 0.75, very similar to before, where 75% of the incoming energy is being reflected. But in the second photo, we can see that the surface has melted into this melt pond with thin ice below, and so the albedo has been reduced a lot to 0.14. So now only 14% of the incoming energy is being reflected. This has big implications because the rest of that heat and the energy is being absorbed into the melt pond and in the ice, but also into the ocean below. So melt ponds have been called the skylights of the Arctic, and that's partially because this low albedo helps them to provide a window of light for living material within and beneath the sea ice. However, the albedo of these ponds has not been very well resolved, so these observations will be used to update our understanding, which will hopefully give us better insight into projections of not only Arctic sea ice, but also what happens in the ocean below and the implications for our global climate.